kind of, y'all ready? Yeah, if you would, I won't take up any more time than is necessary. When we're done, okay? All right. So, we're on it. You know, we began talking about, in the very beginning, the life of a star. Like, what's a star? What is a star? What is it made of? What are its layers? What's it doing? What is fusion? What is all that stuff? Okay. Then we talked about the main sequence, because that is the bulk of a life of a star, and comparing different stars and understanding, okay, you know, everything comes down to its mass, its brightness, its color. Everything is about how big it is. Okay. Then, in some ways, we kind of started back over a couple class periods ago. How do we get a star? And that's really the sequence that we're on, and we're going to be in for at least another 1 or 2 classes of just looking at the life of a star. A star begins as a nebula, a lot of gas and dust. Within that nebula, you'll have more dense regions called filaments. Within those filaments, you'll have even more dense regions called thank you. Sometimes the brain just. Within the clump, you'll have a more dense region called a core. If that core gets dense enough, it has enough material, it will begin to form what's called a protostar. Remember, all of these have this angular momentum, and they're spinning, and there's energy in them, right? And that causes some stuff to happen. And we've drawn this a couple times. I'm going to draw it again. I'm going to give you it won't be today. I thought about doing it today, but I'm like, no, we need today's lesson, then I'll put all these parts together. I will give you a diagram that you just know, okay, you got to have this diagram memorized, you got to be able to tell me what's going on, okay? But, you know, you begin with a nebula. Within the nebula, of course, you have denser regions, right, called strands. This is really, by and large, what a nebula is made up of. Within those strands, you're going to have denser regions called clumps. And then if I were to look at those clumps, I might see some cores within those clumps. Those clumps, as they accumulate mass and they're spinning, they will form kind of a protostar. Right? It's going to have a central clump to it, but because it's spinning, it begins to kind of flatten out and form what's called an accretion disk. If I were to look at this on end, I would see a very, very dense core, and then I'd see something that kind of looked like Saturn if I were to look at Saturn's rings on end, okay? Now, as this develops, these intersections here accrete, it's called an accretion disk, they accrete to the star, right? And so they begin to disappear because they get sucked into the star's gravity. The star gets bigger, denser, hotter, smaller, even as it's getting more material, because the more material it gets, the more gravity it gets, the denser it gets, the smaller it gets, the hotter it gets. At some point, it's dense enough, hot enough, big enough that nuclear fusion will commence. And at that point, we are on the 2 words, main sequence. There we go. Now I've got this other material out here, right? And this material will become planets. This is a planetary accretion disk, right? And so you get same idea here, where you get more dense regions, you get stuff like that here, right? And most of this material is going to get ejected. A lot of it's going to get accreted, and the little things in here, the little protostars or protoplanets, no, they're called planetesimals. They grow and they interact with each other, and their own orbits and their own gravity begin to affect each other, and the orbits change until they settle down to something more like what we know of our planets, right? They think that all stars form just like this, which is why it's reasonable to think that every star would probably have planets at some point. If they all start like from this kind of a deal, then they should all get this, right? Of course, we can't see all of them, because you can only see this if you're looking at it from, we talked about how if you're looking at a star, right? And here you are looking at it, here's you, and a planet passes between you and the star, there's going to be a slight dip in the luminosity. Right? And so if I were to graph it, looking at it, I might see, here's the luminosity, I might see this little dip every time the star passes through. Right? If there are multiple stars, there will be different patterns in these dips. But if I'm looking at this star and this planet's going this way around it, I would never get that dip. And so the star could have a planet and I would never know it. Okay? Not based on this. There are other ways, but certainly not based on luminosity. Okay? So, that said, nebula, filament, clump, core, protostar, accretion disk, planetary accretion disk. Somewhere in here, we're getting into nuclear fusion and we're on the main sequence. And for the bulk of its life, a star will be on the main sequence. Okay? That's a fact. Now, we need to talk about a couple of other things real quick. There are two primary forces at play within every single star. What is it that keeps the star together and provides its initial heat and energy?
Gravity.
Gravity. If all I had was gravity, then every single star would end up as a... We haven't taught this yet. I'm just wondering if you...
But you blow up.
A what?
To blow up, explode.
Well, if it had so much gravity that it couldn't even... Maybe it already had exploded.
Black hole.
And then it was a black hole. Okay? But there are forces other than gravity, because not every star is just contracting in infinitely, right? So, there's this idea of for every force there must be, for every action there's an equal opposite reaction. If a star is stable, and yet gravity is constantly pushing it in, that means something else must be pushing it out, and that something is?
Pressure.
Pressure, right? So gravity's pushing in, pressure's pushing out. I am drawing gravity I'm drawing pressure in red because that pressure comes from the heat that's happening in the core. Okay? So heat, pressure. Heat is causing this pressure. It's pushing out. Gravity is pushing in. During the main sequence phase, these two things are more or less balanced. During its main sequence phase, what does it start doing? Fusing hydrogen into helium. Okay? So, taking hydrogen, making helium, we release a little bit of energy, right? In the form of light and heat primarily. Very low percentage of this becomes light and heat though. It's like 0.8% or something like that. 0.7% of its mass is converted to energy. That's it. Okay? 0.7% of a star's mass is ever converted to energy. So you may hear about a star burning through fuel. Well, if you burn through fuel in your gas tank, eventually you're going to be on E, right? There's like literally going to be nothing left. It's not exactly what we mean with stars. As they burn through hydrogen, it's not left with nothing, it's left with helium. So if 0.7% is converted into energy, then that means that like 99.3% of the mass still remains. It's just not usable as the star sits for nuclear fusion. Okay? It exists. It was in hydrogen, which is pretty easy for it to use. But now most of its bulk is at least in the core where the fusion's happening, because the whole star is made up primarily of hydrogen, right? But the fusion only happens in the core, at least during the main sequence phase. Okay? But 99.3% of it now, the mass exists as helium. To fuse helium into anything else requires a ton of energy. Okay, it's got to be extraordinary. Okay? So again, as we talk about them burning through fuel or using up hydrogen, it doesn't mean that it's just gone. It's just been converted into a form that's not as easy to use. Okay? So, the bulk of its life, come on over here. You gotta push, you gotta really push. You gotta actually push. Okay? Most of its life, it's in equilibrium. Okay? Maybe what we might call dynamic equilibrium. There's a little bit of movement back and forth. Just a little bit, right? And you think about it, every day, that star is losing a little bit of its mass. Right? So if you're pressure and I'm gravity, every single day he's just ever so slightly pushing me back, right? Because there's going to be more pressure than there is gravity. That makes sense, doesn't it? Until one day, I mean, what creates this pressure? The heat, the fusion. Well, every day I'm losing a little more of my hydrogen, right? It's getting converted into helium. Eventually, all of the hydrogen in the core will be converted into helium, right? Agreed? Okay, let's go here. So you're winning because, you know, there's more pressure than there is mass, and so you got to do this. So you want get out of here. So anyway, but one day there's nothing else to create that pressure. Right? Right? And so he's going to get pushed down by gravity. He's going to get a lot denser, and that heat, that pressure from the gravity is also going to heat it up a lot. Make sense? Not that much. That comes later. But you are right. So let's go back. Let's do this. Here we are. This is most of its life. What stage is this in? Main sequence. As it's running out of hydrogen, the pressure is going to be winning until we run out of stuff. And then very rapidly, I'm going to begin pushing in, right? He's going to get denser. As I keep pushing and pushing and pushing, now he's going to begin to heat up, right? Does that make sense? Oh, when he heats up, what's he going to do? He's going to start pushing back, okay? One of the things that happens here is now, this is all happening, well, let me do this. Think about a star. It's got layers, right? What's the innermost layer? Core. This is where the fusion's happening, right? Core, what's the next layer? Oh, it's been a little bit. Okay? I got the radiative zone.
Convection zone.
And I've got the convection zone. I've got the photosphere. And then I've got, which one? Chromosphere. And then, of course, I've got corona. Good. Okay. So, all of my fusion happens here during the main sequence. But when I run out of hydrogen, this core is going to shrink because of more gravity than pressure. And it's going to be made up of helium. Okay? But as it shrinks, it heats up. Like a lot. Okay? It heats up so much that this layer out here that for its entire existence was on the edge of doing fusion. If it had been doing fusion, we would have called it the core. But it wasn't doing fusion, so we didn't call it the core, we called it the radiative zone. All of a sudden, all this hydrogen that was here gets crazy hot because of all the heat coming out from here. Well, when it does that, what does it do? If it was on the edge of fusion and now it gets hotter, what happens to it?
Pressure is good.
And it starts to do fusion. If I was, think about it, if you got a pot of water and it's like right on the edge, like you can see the steam coming off, but it's not boiling. And then you turn up the heat, it's going to boil. It's the same idea here. I've got this layer that's right on the edge, and I heat it up, and now it's going to begin to do fusion. So now I got this process happening somewhere else. I'm doing fusion out here. Come on. I got gravity, I got pressure, all of a sudden you're doing fusion. What are you doing to me?
I'll push it.
You better push. All of a sudden he's pushing me way out. And now my star begins to grow. Okay? And we begin to go through these cycles. And so a star will literally get bigger. Now I want you to think about some other factors. As I get big, as you push me out, I'm further away from the core. I'm further away from any fusion. I'm going to get hotter or colder? I'm going to get colder. So the star's going to get bigger, but the surface is going to get cooler. And yet because there's so much surface area, the whole thing gets brighter. Think about this. Come over here. So let's do our AHR diagram, okay? You're in the way. I'm going to erase. Can I erase this one? Let me erase this one. We'll do it here. This is on camera, that isn't. So. All right. So HR diagram, right? This is luminosity. This is temperature, right? Think of a star like our sun, right? Right about here. Well, when it gets to the later stages of its life cycle, it's going to get bigger, right? But as it gets bigger, the outer layers are going to get cooler. The inner layers will be crazy hot, but the outer layers are so much further away from it that they get a lot cooler, right? Cooler is this side, right? So it's going to move this way. Yes? Well, because there's so much more surface area, it's going to have more light escaping out, so it'll get a lot brighter. Brighter is up here. Where do I find my red giants? Up here. Make sense? So it's bigger. Now, I say bigger, I don't mean more mass. I mean more volume. The volume just gets... So my volume goes up. My temperature, because of the outer layer, I'm going to say surface temperature goes way down. But my surface area, which is related to my volume, which lets out more light, goes way up, right? So what did I say there? Surface area, which equals light, right? Escaping, it goes way up. And so this is where it was on the main sequence. A star like the sun, when the hydrogen is used up in the core, and the core collapses a good bit, not completely, but a good bit, it condenses, helium's there, and it's just getting crazy hot. It ignites this next layer, which begins fusion, which creates pressure, which pushes those layers out, so my star gets much bigger, less dense, but much greater volume. The surface temperature goes down, so we move towards the red area. Surface area goes way up, so even though we're redder and cooler, there's more light actually escaping, and so we go to this area up here. And this is what accounts for our red giants. Okay? And again, just to hit this home, all this is because you've got just really two forces happening in here, right? We've got gravity and we've got pressure. During the main sequence phase, they're in complete harmony, right? But then, as I'm dying, you win for a little while, but then quickly I shrink you down. The next layer ignites because of all that heat, and now you really push me way out. We get much bigger, much redder, much brighter. Okay? All right. Well, let's watch some videos and talk about some things. What is that?
Turn it off.
I thought I was good and I wasn't. Here we go. That's Dvorak's cello concerto. Okay.
In this video, we're going to describe the evolution of stars from main sequence to the red giant stage. We've mentioned before that all stars become main sequence stars after their protostar stage. They become a main sequence star when two things occur. When nuclear fusion reactions are sustained in their cores, that is, that when they turn hydrogen into helium in their core, and they keep that process going. And that sustained fusion keeps a balance between gas pressure, which is tending to push outward of the star, and gravity, which is tending to push inward. When those two pressures are in balance, a star is in hydrostatic equilibrium, and it is a main sequence star. Most stars are main sequence stars, and this is because they spend 90% of their lives in this state. And so when we look out into space, most stars that we observe are going to be in this stage of their lifetime. All of this time turning their core hydrogen into helium. And that's the fuel that they use to sustain their energy generation and this balance between the competing pressures. But when the hydrogen fuel in the core runs out, that's when a star is no longer a main sequence star and it becomes something else. When a star leaves the main sequence, that is, when it finishes using up its hydrogen fuel for nuclear reactions, it becomes out of balance. There is no longer a sustained set of energy generating processes to counteract the crushing force of gravity on the inside of the star. And so the competing pressures are no longer in balance, and eventually something has to keep a star from collapsing in on itself. So what's happening on the inside of a star? When the hydrogen is completely converted into helium in the core, then you've got less gas pressure pushing out. And that's demonstrated, or at least depicted in this diagram, where we have a balance between forces on the left. That's the main sequence star, where gas pressure, which is the arrows pointing outward, is balanced with gravitational pressure, the arrows pointing inward. And then on the right side, we've got the follow-up situation. When the hydrogen fuel has been used up, now the core will have less sustained energy generation and eventually none. And so the arrows pushing outward will not have as much pressure compared to the inward gravitational pressure. And so there won't be a balance, and the net pressure will be inward. The star will effectively get smaller, it will begin to collapse. So what happens to the core? Well, we have to differentiate between the outer layers and the core of the star. The core itself will be completely helium. That helium is not fusing into any new elements at this point, but it's still extremely hot. Gravity is going to crush the helium atoms into an even smaller size, and as that occurs, the helium core will get hotter, denser, and will eventually begin fusing, but not yet. The outer layers will also collapse down onto the core. The outer layers of the star are just hydrogen atoms which have not, to this point, been fusing. while the core is collapsing into a very dense hot ball of helium, the outer layers are compressing a very dense layer or shell just around the core. This is just hydrogen atoms, but they get so hot and so dense in that shell around the core that they begin fusing. And it's even hotter than the core of the star was before. The hydrogen fusion that begins in this shell is happening at such a fast pace that the outward gas pressure that results from this shell fusion makes the outer layers of the star expand even further than they were when the star was a main sequence star. And so the star will expand, and because of this, on the outside, as it gets larger, it will become brighter than it was before, and it will also lose some surface temperature. Eventually, the core of the star, which is all helium at this point, will collapse down to the point where its temperature is in excess of 100 million Kelvin. At this point, the helium atoms can fuse into carbon and oxygen. And so you get a new set of nuclear processes. This isn't hydrogen into helium, this is helium into carbon and also helium into oxygen.
Okay. This stage is full-blown red giant that he's at right here, okay? That makes sense? I mean, it's completely off the main sequence. It's fully up, it's fully up here. Stage. There's a little bit of a transition period. I'm sure he'll show this in a minute. You look at a star, say like our sun, it kind of does something like that. Our main sequence, of course, we know it more or less looks like this. Every star begins somewhere on here. They don't change position on the main sequence. They do change position on the Hertzsprung-Russell diagram. Slowly, as they lose temperature, right? They'll start to become redder, but they'll get bigger, so eventually they'll land up here, and they'll sit here for however long as they're fusing helium into carbon and oxygen and things as it's describing up there. All right? So I just say this to say this is full-blown red giant stage that he's talking about.
And so what are the net reactions? You have 3 heliums can fuse into a carbon, you get some energy.
You don't need to know this
or
right
you can
now.
also have a carbon plus a helium and build an oxygen. And you also get energy out this way. These reactions are going to happen at a much faster pace than the hydrogen to helium reactions that were occurring during the main sequence lifetime of the star. And so later on, in what we call the red giant lifetime of the star, we've gone from having a star expanding and getting larger while the core is crushing down and getting smaller. Eventually, the interior of the star will have layers that look like this, where there's a core represented by the black dot in this picture. That's where the helium fusing is taking place, the helium fusion. Helium is fusing into carbon and oxygen nuclei. Around the core is a hot, dense shell of hydrogen material, and that material is fusing, generating an outward flow of energy. That is sustaining a gas pressure which has pushed the outer layers of the star much farther out than they were before. And the outer layers are still just hydrogen, and those far outer layers are not fusing into any new elements. When a star has expanded to this point, it's much larger than it was during the main sequence lifetime. The image that I'm showing you here shows the sun as a main sequence star relative in size to a few other stars, Sirius, Pollux, and Arcturus. But let's take a look at these stars compared to their red giant analogs. So the sun in this new image is just 1 pixel in size. But look at Betelgeuse and Antares. These are red giant stars. These are stars that have expanded after the main sequence lifetime to tremendous sizes. Betelgeuse and Antares are so large that if you were to place them in our solar system, where the sun is right now, their layers, their outer layers, would extend beyond the rocky planets. We can also depict this change in properties of stars on the HR diagram. We have a main sequence that is depicted in this HR diagram, represented by the bold diagonal line. And along this line are star symbols.
Okay, so this black line is, we're used to seeing this stretch out quite a bit. They've kind of condensed this for space. They're saying this is the main sequence. Down here we'd have, the red dwarfs. Up there you'd have the blue giants. Our sun would be right here. Every star is somewhere along this black line for 90% of its lifetime. But then, after the fusion of hydrogen to helium ceases, what happens to it? And so it's showing you the line. Something like a little less than our star, it is going to get much brighter, right? I mean, magnitudes brighter. And it's also going to get a little bit cooler. Something up here, like a blue star, it's not necessarily going to get brighter. I mean, it was already huge and bright, but it is going to get a lot cooler. And notice this one, it looks like one of my kids just came and scribbled on it, right? It's moving back and forth quite a bit. And that's because the pressure and the gravity is happening quite a bit. Huge fluctuations. A small star, very little fluctuation. It's much more gradual. Something twice the size of our sun, you see some significant fluctuations. You get up here, huge fluctuations, okay? And that's having to do with the interplay between gravity and pressure. I don't need you, I want you to look at it, and I'm going to give you this. I don't need you to memorize this at all. But if I give you this,
Understand.
huh?
Understand.
One more time?
Understand that.
All I really want you to do is to look at it and go, well, this is a star leading the main sequence.
Okay.
That's it. I don't personally see any value in you memorizing numbers and too many things going on here. But to understand, a star doesn't move on the same main sequence, but it does move off of the main sequence. So I give you a diagram like this, and I go, what is that showing? And you need to literally just be able to tell me this is a star leading its main sequence. Okay? I might give you something like, hey, what's this and what's that? Okay, that's its giant stage, that's its main sequence stage.
Is that represent main sequence stars of different masses. And so our sun would have a main sequence mass of 1 solar mass. There's a star of 2 solar masses, 5, 9, 30, and so on. The other lines, the other colored lines that are represented here on this HR diagram are the property tracks of stars of different masses after they finish their main sequence lifetime. So for a star that is about half the mass of the sun, I'll point to it here, it's labeled as MS. This star will expand after its main sequence lifetime. And as it becomes larger, it will become brighter, and it will also decrease very slightly in surface temperature. So as we follow its life track into the main, after the main sequence, into the red giant branch, it will go up in luminosity. And that's because it's becoming brighter. A star that is 2 times the mass of the sun, so not much more massive than the sun, will begin as a main sequence star on the bold line, and it will go to the right, decreasing in surface temperature, but eventually will increase in luminosity. What happens here is that this star will eventually expand to the point where its decrease in surface temperature on the outer layers are different from what's happening in the core. The core will eventually begin fusing helium into carbon and oxygen. And when that occurs, the star will truly be a red giant. More massive stars have different life tracks. they can go beyond the fusion of helium into carbon and oxygen, and they can fuse even heavier elements, but we'll talk about that in another video. However, their life tracks take them from extreme luminosities to similar luminosities, but very low surface temperatures. And so I've circled here the life track, which is most similar in this image to the life track of a sun-like star. Here's another schematic of the different layers that you would have in these different times during after the main sequence lifetime of the star. You would have hydrogen fusion in the core. That's hydrogen and helium. And then you'd have a helium core after the main sequence lifetime. There would be a hydrogen shell that develops around that, and that causes the outer layers to expand to a larger size. Eventually, that shell fusion causes the star to expand to such a large size that it's extremely high in luminosity. However, when a star begins helium core fusion, the outer layers will contract down very slightly, and so the red giant star, when it finally becomes a helium fusing red giant, is just slightly smaller than before, and so it'll lose a little luminosity. But a red giant is a red giant when it is fusing helium into carbon and oxygen in its core. And so this is the life of a star after it has finished its main sequence lifetime. Also, another thing can occur. When a star becomes a red giant, during this process, it's expanding out, but gravity may pull some of the layers back inward. And when that occurs, some of these inner layers will get hot and denser and will cause an increase in the energy generation on the inside of the star. This will cause the outer layers to want to expand again, and gravity may pull back. This oscillation between gas pressure and gravity can cause a star, a red giant star, to be what we call a variable star. And so it will get larger, it will get smaller, that will result in it appearing brighter and dimmer over time. All of this is regulated by the interior temperature, the density, and what we call the opacity of a star's atmosphere, the ability of photons to move freely or less freely through the atmosphere. There are three types of variable stars that a red giant might become. So they are RR Lyrae variables, Cepheid variables, and Mira variables. These are based on how long of a period the variability is happening in. So RR Lyrae variables, the brightening and dimming of an RR Lyrae variable.
Let's stop there. So 90% of its life is spent on the main sequence. So if I were to draw a graph of the life of any given star, right? Start off, I'm not a star, so this is going to be time. Okay, this is going to be location. I am very quickly going to come up to being on the main sequence, right? And I'm going to stay here for a long time, right? 90% of its life, right? So it's not that important, that's not that complicated, right? Got several other things that we want to think about though. True or false, the red giant has no hydrogen?
No hydrogen.
True or false, does it have hydrogen?
No, it's fused into helium.
False.
I don't think so.
Where is it all fused into helium?
During the main sequence.
Yeah, but where in the star does the
In the
fusion
core.
happen? Only in the core. So while the core has become helium only, there's still hydrogen everywhere else, which is why it's able to ignite fusion in an outer shell, which creates that pressure, which pushes it way out, okay? So this is just a kind of a concept check. A red giant definitely has hydrogen. just not in the core, okay? All right, okay. I want to give us some other just concepts checks. All right. This is going to be time. I draw these, okay? This can be time. Let's do pressure. What do you know about the star and its time? 90% of its time is in the main sequence. What's true of pressure during the main sequence? Think about pressure and gravity. Come on.
Equal.
It's pretty balanced. Pressure doesn't change a whole lot during the main sequence phase. It's going to remain steady. So for about 90% of this, it's going to be pretty much a flat line, right? Before I begin fusion, do I have pressure? No, because pressure is created by fusion. So most of its life, I got almost no pressure, right? I mean, really, very little. Okay, and then all of a sudden we jump up very rapidly once we hit main sequence. This is when fusion begins. When I run out, right? Come on up. When I run out, right? Now there's no more fusion, right? And so I begin kicking your butt. So what do I do with my pressure here?
Goes down.
It goes down pretty rapidly. But as this goes down and gravity begins to win and push everything in and I begin to ignite, then
More pressure.
more pressure. And we're going to get much bigger. Right? Until we fuse everything else we can, and then the star will either explode or fade away, but either way, we're going to lose all that pressure, right? And it's going to contract. Is there any pressure in a black hole? No. I mean, it's just, I mean, not appreciably, right? So, that's what I hope. Well, you need given phase. This is the end of its life. This is relevant. There's nothing quantitative about this. This is purely qualitative, relatively speaking, what's going on. Okay, so this is a graph of pressure over time. 90% of its life is going to be steady. We're going to build pressure quickly as we get into fusion. We run out, we're going to dip, then we're quickly going to rise back up. What stage is this?
Red giant.
Red giant. That's okay. Here's the kind of stuff you got to be able to interpret something like this. This is red giant, right? This is main sequence. This is end of life, right? And so that depends on what kind of how big a star was. We're not to that point yet, but I just want us to think about these two features, okay? Let you draw that for a minute if you're up for it, or take a picture. Somehow get this, okay? Even I'm going to take a picture because I need to remember what I have to be able to give it to you. Okay. All right. Everybody good? Let me do another one. Let's do luminosity. Okay. We're going to do it for a star like our sun. Start off gas, get up to nuclear fusion. Most of your life is spent on the main sequence. Run out of fusion, which means things aren't producing the same light. What's going to happen to my luminosity during those early days? Is it going to go up or down? If I'm not producing any, if I'm not doing fusion, it's going to go down. Briefly. But then, once I expand, right, my volume increases greatly, my surface area increases greatly, what's going to happen to my luminosity? It's going to, think about where your red giants are. They're up, right? They're way up. So it's going to go like, so, you know, there's usually a little bit of a dip as it contracts slightly. And then, depending on my end of life, you know, I may do something. This is variable, okay? I'll just kind of draw it like this. Okay, so what phase is this? Red giant. And then this is going to be end of life. Okay, so this is luminosity over time, right? Let's do this. That's the, okay, yes. Now we're going to do volume over time. Got to change the start. How do these things begin? Huge, huge balls of gas, right? And then it's going to contract down into a main sequence star, right? Then, as it runs out of fusion, it will contract quickly, but then it will expand exponentially to the red giant phase until something happens at the end of its life. Of course, it could, if it's a, you know, if this is like a blue supergiant, the end of life here is on this axis, right? I mean, it's a black hole. There is no appreciable volume. It's just a point. Okay. All right. Times. We're good. Okay. This. Do me a favor, stand up. If you don't want to, I'm going to have you guys do the thing where you're pushing against each other. If you really, like, you're not comfortable with that, or you're like, I hate this and I want to run away, you can run away, you can leave if you want right now, or you can sit. I do think it will be helpful for you if you stand up and participate, okay? This will be the last thing we do. When I taught high school for 10 years, I made them get up. We tossed ping pong balls, practicing electronic bonds. I had dances we did. It helps. I went through ATP synthesis. Looks kind of like the sprinkler. But, this is it. This is all I got that's going to participate on. Okay.
Come on.
All right. Felipe, come over here. You go with him. You're going to go with Jacob. All right. Find yourself a spot. Going this way. All right. Okay. This side is going to be pressure. This side is going to be gravity. All right. At the beginning, before it's a star, what's happening? Where should we be standing in relation to each other?
Same.
Oh, y'all need to move. This before it's push your chairs in, or this isn't going to work out. Okay. All right, ready? Before we're a star, we're just a cloud or we're just a protostar. Where should this pair be standing?
There.
In the middle?
In the middle.
There is no pressure though. No pressure. There's no fusion. We're sitting here, and what's happening as the gravity's increasing and there's no pressure yet, what's happening to the star? It's heating up. It's heating up. until eventually nuclear fusion begins, and then where should we be? We should be in the middle, right? And now how long, if we were to do this for 10 minutes, how long should we be standing in the middle?
One, 9
Oh, no.
9 minutes, 90% of its life, right? Yeah, y'all got it, okay. And somewhere around like 9.5 minutes, think about that. Or around 9 minutes, maybe 9 minutes. For about 9 minutes, what should happen? What should happen now?
Start pushing down.
Well, what happens to my fusion?
Stops.
So now,
Start pushing.
I start pushing harder. But then he's heating up. And so then pressure begins to win. And now I go here, right? And we'll do a little bit of this back and forth a little bit, right? Until eventually, at the end of its life, there's nothing left to fuse, and then hopefully, let's do it again. One more time. Y'all should have done this. It's helpful.
We're lucky.
All right. Before we're a star, where do we need to be?
Almost done, we do some
Huh? That way.
Yeah, we're good.
Let's go.
So,
Okay. Nuclear fusion begins. Where do we go? Middle.
Middle.
Okay. Good. How long do I stay here in 10 minutes? 9 of them. Then
Go back to the right.
I got to go this way because we lose our fusion for a second. We heat up and then fusion begins and pushes us way out, right? Now we kind of stay here for a while until we're out again and then all the way back. Okay? All right. That's it. That's good stuff. Let me pray for us. Pray that we remember all this.
Almost wanted to sit down.
I'm going to go ahead and pray for us. Gentlemen.
Ricardo, Puyo.
Gently. Lord, help us to retain these things that we've learned today. Help us to come back to our remembrance in time for a test, Father, but also just for the rest of our lives to understand something more of the universe that you've created, your awesome power and your glory. Father, may you receive praise because of our mere presence here in this classroom. We pray this in Jesus' name. All right. See y'all next year.